Accuracy and precision. Have you ever measured something over and over and got different numbers every time? Or wondered why results that look consistent can still be totally wrong? Today, we're breaking down what these terms mean, what causes measurement errors, and how to check if your results are reliable. What causes measurement error? No measurement is ever perfectly exact. There's always some error. There are two main types. Systematic error comes from faulty tools or using them incorrectly. For example, a scale that always reads too heavy, or reading a ruler from an angle instead of straight on. It pushes all your results the same wrong way. Random error comes from small, unpredictable changes, like temperature shifts, your hand shaking slightly, or tiny fluctuations in the tool. Your results vary up and down by chance. Accuracy versus precision. These sound similar but mean very different things. Accuracy: how close your measurement is to the true, accepted value. Precision: how close your repeated measurements are to each other. Key rule: you can be precise without being accurate. Think of throwing darts. All over the board, not precise, not accurate. Spread out but near the center, accurate, not precise. Tight cluster far from center, precise, not accurate. Tight cluster right on the bullseye, both accurate and precise. How to check and improve accuracy. Reduce systematic error by using tools properly and calibrate instruments regularly. That means checking and adjusting them to match standard values. To measure how accurate your work is, calculate percentage error with this formula. Percentage error equals experimental value minus accepted value divided by accepted value times 100. Example: you measure a sample as 14.90 g. Its true mass is 15.00 g. Percentage error equals 14.90 minus 15.00 divided by 15.00 times 100 equals 0.67%. A small percentage error like this means your measurement is very close to the true value. Since every measurement carries some uncertainty, significant figures help you clearly show which digits are reliable and which are only estimated. Every measurement has some error from systematic or random causes, so significant figures tell others exactly how precise your result really is. For example, if you measure a pencil between 7.5 centimeters and 7.6 centimeters, you can write 7.55 centimeters. The first two digits are certain, and the last one is your best estimate. Even tools like an analytical balance that show 4 decimal places only reflect how many digits you can trust. Here are the rules for counting significant figures. 1. All non-zero digits are always significant. For example, 143 grams has 3 significant figures, and 987,654 meters has 6. 2. Zeros placed between non-zero digits are significant. For example, 2005 liters has 4 significant figures, and 101 kilograms has 3. 3. Zeros before the first non-zero digit are not significant. For example, 0.001234 meters has 4 significant figures, and 0.0234 kilograms has 3. An easy way to remember: start from the left, skip all zeros until you hit the first non-zero digit. Everything after that counts. 4. For numbers greater than 1, zeros after the decimal point are significant. For example, 2.00 seconds has 3 significant figures, and 750.00 km has 5. 5. Trailing zeros with no decimal point are unclear. You can use scientific notation to make them clear. 9,000 grams has 1 significant figure. 9.0 times 10 cubed grams has 2. 9.00 times 10 cubed grams has 3. And 9,000.0 grams or 9.000 times 10 cubed grams has 5. Significant figures in calculations. Your knowledge of significant figures also applies when you add, subtract, multiply, or divide measurements. Here are the rules. 1. Addition and subtraction. Your final answer must have the least number of digits after the decimal point from the numbers you used. Example: add 23.456 grams and 2.78 grams. First, line up the decimal points. Add normally to get 26.236 grams. Compare decimal places. 23.456 grams has 3 decimal places. 2.78 grams has 2, which is the smaller number. Round your final answer to 2 decimal places. Final answer, 26.24 grams. 2. Multiplication and division. Your final answer must have the least number of significant figures from the numbers you used. Example, multiply 87.32 meters by 1.78 meters. Multiply normally to get 155.4296 square meters. Count significant figures. 87.32 meters has 4. 1.78 meters has 3, which is the smaller number. Round your final answer to 3 significant figures. Final answer, 155 square meters. Important note, exact numbers, like defined conversions or counted values, have unlimited significant figures. You do not use them to decide how many significant figures your final answer should have. Only your measured values count. For example, one stick is 2.67 meters, which has 3 significant figures, and you have exactly 6 sticks. The number 6 does not limit your result. 2.67 meters multiplied by 6 equals 16.02 meters, so round to 16.0 meters to match the 3 significant figures from your measurement. Conversion of units. Most measurements of the same quantity can be written in different units. For example, a mass of 3,500 grams is exactly the same as 3.5 kilograms. You can convert one unit to another by using the prefixes added to the base unit, such as gram. There are 2 simple ways to do this, moving the decimal point or using the factor label method. By moving the decimal point. This method works only with metric units and their standard prefixes. The key rule is, if you are changing from a smaller prefix to a larger prefix, move the decimal point to the left. If you are changing from a larger prefix to a smaller prefix, move the decimal point to the right. Example 1. Convert 14 centigrams to kilograms. From centi to kilo, you move 5 places up the prefix scale, so move the decimal point 5 times to the left. 14 centigrams, 0.00014 kilograms. Example 2. Convert 56 kilograms to centigrams. From kilo to centi, you move 5 places down the prefix scale, so move the decimal point 5 times to the right. 56 kilograms, 5,600,000 centigrams. Even though the metric system is now used almost everywhere in the world, some countries still use the English system. You can convert units back and forth between these 2 systems using these standard conversion values. Length, 1 inch equals 25.4 millimeters. 1 foot equals 0.3048 meters. 1 yard equals 0.91444 meters. 1 mile equals 1.609344 kilometers. Volume, 1 cubic inch equals 16.387064 cubic centimeters. 1 gallon equals 3.785541 liters. 1 fluid ounce equals 0.0295735 liters. Mass, 1 pound equals 0.453924 kilograms.